All right. I think that we're rolling. Fine. Seems like this should be easier.
Was Ghost Guy last round? Just not by a long way. I saw the MPI posters edition. This is
Pod A, right? Pod A. 3873. 3873. Connect. Connect. Okay. So while I'm fixing this, any groups have any questions about the project you want to start with? All right, go for it. What's the question?
Does our item necessarily need to be competitive in the market?
Does your item need to be competitive in the market? Give me an example.
Like how much do we have to worry about driving, about looking at other things other similar items in the market, other alternatives, and
so yeah, I think I get the gist of the question. So it's not a marketing class, right?
Okay.
And it's not an entrepreneurship class. So it shouldn't be ridiculous, but you don't have to worry about whether or not what you say is going to drive sales is valid, right? I'm not going to criticize that kind of a thing. It's really about, if you could sell this product, what would it cost to create the company to make the product and then start selling it? I suppose if you could convince me that you could design a time machine and that you could make it with a CNC machine tool, and maybe I'd believe you, but it'd be a tough sell for like a time machine, or like Spider-Man has the things on his wrist, right? And he does this and it shoots out the web and stuff like that. If you were going to make something that was like a toy that was to be like that, I would believe it. If you said you were going to actually swing from building to building down the city streets, I wouldn't believe it. So it should be reasonable, but it's not a marketing class. It's not a class about entrepreneurship or anything. So just pick something you think you could make and that it would be fun to have the project be about. Does that make sense to everybody? All right, StreamYard, enter studio. Mute one of these. Let's mute that one. Hey, did it still do it? Not quite as much. Let's mute this one now. Now is it still echoing? Good, no echo. I'm gonna have this one not sort of be there. Then it's this one, okay. And the problem was I couldn't share the screen. So let's see if I can share the screen now. Three 3837. Hey, that works. Okay. ME1800 syllabus. Today's lecture. This one is today's lecture. Lecture slides, yeah. So this will teach me a lesson. I won't try to use the computer that they provided for the classroom. I'll just continue to use my laptop. All right, now you guys still can't see it, but I can fix that. App window, this one. And now, I think the people in the room and the people online can see the screen share. Share the screen, share this one. Window, Chrome tab, how about this one? Share. All right. And so now I think all right. Outstanding. So much fun. Technology. That's not the screen I want you to see, though. That's the screen I want you to see. Sweet. All right. 15 minutes. Maybe how much that cost? 15 minutes. How much do you guys pay per minute to be here? Have you figured that out? Has anybody figured it out? Anybody do that? I used to do it as the first homework assignment in ME1800, especially A term, because there's a lot of you get software as a freshman A term. I used to give this as my first homework assignment in ME1800 was to calculate how much it costs you per hour of learning time when you come in computers. What if you want to do some sorting for glucose and amino acids? So anybody who knows? Well, so there's not only 72 people in the class. And when I did the math, it came out with if you assume that people pay tuition and then pay the average housing, and that everybody in the class paid, if you calculate the number of hours we expect you to be here, I have to deliver about $10,000 worth of content every hour that I'm teaching. So collectively, for the hour here, you guys have paid $10,000 for today's hour. So that's pretty exciting. So you guys should, for those 15 minutes we spent futzing around with the computer there, you should all donate your money back. All right. So yesterday we were talking about prototype machining, CNC, and why we're going to use CNC machining for prototypes. And of course, we do a lot of prototype machining here at WPI, right? There's a lot of class projects. There's a lot of IQPs and SQPs here at WPI. And so the other reason we emphasize using CNC machining to do prototypes is because we have a lot of access to CNC machining here at WPI, and it's easy for us to do that stuff. So that's why we emphasize that so much. So if you've decided to use CNC machining to make your prototype, what's the first thing you then as so not the design engineer, as soon as you get to that point and you start doing the machining, you start getting ready to make the parts, even if you are the designer, which often is the case with a class project or with an MQP or something like that, right? Even if you are the designer, at the moment when you start getting ready to do the manufacturing, you need to put on the manufacturing engineer hat. You need to start thinking like the manufacturing engineer.
And so if we've got our design completed, the design is done, and we're going to use CNC machining to make a prototype, what's the first step we have to do as the manufacturing engineer or as the CNC machinist? What's the first thing we want to do at that point? Anybody? You've got the design, so you've got solid models, you've got drawings, you know you have material specifications, you know what it is you want to make. What's the first thing you got to do? Yep. You've got to decide in your mind how you're going to make it. So before you start doing any computer-aided manufacturing, before you get to this free stuff, before you start setting up a machine tool, you've got to in your mind think about how are we going to take this, how are we going to make this thing? Part of how you're going to make it is deciding what stock material are we going to cut out. Now, the designer, when they make the design, they decide what the material properties of the finished part are going to be. So maybe they'll pick aluminum because they want it to be mostly corrosion-free. Right? They don't care if it oxidizes a little bit, but they want it to be mostly corrosion-free. So they pick aluminum, and they don't want it to be too heavy, and they want it to be cheap. And so that all fits with aluminum. So they've chosen that. Maybe they even said they need it to be 6061 T6 aluminum. So they tell you what alloy aluminum it is, what heat treating it needed to get to before it came to you to make the part. So they picked those properties, those material properties. But you as the manufacturing engineer, the machinist, you've got to decide which physical piece of 6061 T6 aluminum we're going to use. So once you decide what type of a process, and so at the high level, we've been turning a mill, right? So if it's an axisymmetric part, we're probably going to turn it. If it's a prismatic part, we're probably going to mill it. And if it's got combinations of both axisymmetry and prismaticnism, that's a word, right? Prismaticnism. If it's axi-prismatic symmetrical, you might do both type of operations. So once you've decided which type of operation is well suited, then you're going to say, all right, which physical piece of stock material are we going to use? And you don't have to necessarily be holding that physical stock material in your hand. A lot of times, especially making prototype parts, running around the machining labs and stuff, we'll actually go out and look around at the stock or like in the scrap part, and we'll say, this is the piece of material I'm going to use. And sometimes we do that before we design the part. Then we design a part that fits inside that piece of material. Yeah, that's critical, right? The part actually has to be inside the material. If the part's bigger than the stock material, probably not the right piece of stock material. You all think that's obvious, right? Totally seen an MQP do it. Totally seen it happen where they think they're going to cut the part and then they realize it doesn't actually fit inside the stock they bought. It sucks when they pay like $200 for the stock too, doesn't it? Okay, so we picked the process, we picked the stock material. What's the next thing you imagine we have to do as CNC machinists, as manufacturing engineers, to get from the art, which is the drawings and the art is the drawings and the solid models, all that stuff that define what the designer wants the part to be. What's the next logical thing you think we got to do to go from art to physical part? Because our end goal, great, especially if we're doing like B2B. If we're machining parts and we're selling other machine shops or things like that, or we're doing prototypes for somebody that's invented something. I used to do a lot of that. So some inventor would come up with an idea, they'd send the drawings for their prototype part. When they send the drawings, they ask for the price. Does that make sense? If it's a commercial transaction, they want to know how much it's going to cost. When they're asking for the price, though, what do they actually want? Do they really want a price? What they actually want is to be holding that part in their hand, right? They don't want the price. They want to have the part. They know there's steps in the process. And so if we're going to make the part, we've got the design, we've decided that we're going to mill the part. Let's pick one. So it's a prismatic part. Maybe it's like this shape. So we're going to mill it. Maybe we're making a case for an iPhone. So we're going to mill the part.
We picked our stock material. We've got a piece of aluminum that's a little bit bigger than the thing we want, so that's good. It fits inside it. You can almost sometimes, especially with prismatic parts, you think of the stock material that you need as like, what's the shoebox that your part fits inside? So if you think of what's the smallest shoebox I can fit my part inside, that's often the piece of stock material that you need. And a lot of times we won't use the smallest shoebox that it fits inside because it's more convenient to buy the stock material in a different shape. So sometimes we get it bigger or something like that. But so we've got the material. What's the next thing we've got to do if we're going to make the part? So we've got material. We figured out we're going to mill the part. We know we've got a piece of material. The part fits inside. What's the next thing we need to do? No matter who we are or what the part is, what's the next step? Yeah. So at some point in the process, we're going to have to make code that the machine runs. So at some point in the process, and that code consists of basically 3 different commands. There's all CNC machine tools basically do 3 different things. I have maybe 4 things. So they spin the spindle. So it's milling a tool spinning in the spindle, right? So we turn the spindle on and off, we set the speed of the spindle. You can actually sometimes in some machines you can set how fast does it accelerate or decelerate, all those kind of things. But they spin the spindle. The reason we spin the spindle is to enable cutting to happen, right? The next thing that we have to do with our CNC machine tool is we have to move. I used to always say from point A to point B, right? Because you feel like if you're moving to point B, you have to have been at a point A. That's sort of intuitive. So I used to like draw on the board or stuff. And like, you got to move from point A to point B. Point A, point B. It turns out the command that is given when you want to move from point A to point B does not care about point A. The only thing you can command is where do you want it to move to. And it will move from wherever the hell it is when it gets the command to the point you told it to move to, even if there's something in the way. So that's something to remember as you're doing this. But so we can move from wherever the hell we are to point A in a straight line at a controlled speed. We call that a feed move, a linear feed move. Linear because it's a straight line. We're not that inventive with words. So we can move from point A, or we move from wherever the hell we are to point B in a straight line. It's a linear feed move. So we can spin the spindle, we can move in a straight line at a known speed. We can move to point B, say where's point B? Right there? The little plate on the floor. So we're going to move to point B as fast as we can possibly get there. We call that a rapid move. Turns out, again, not very inventive. We don't control the speed. It's as fast as the machine can move. And we don't control the path. So it seems like a straight line is the fastest path, right? It is the shortest distance. That's typically not how these CNC machines work. Typically what they do is they move from point A, they move from wherever the hell they are to point B. If we're doing a rapid move, say it's got to move in X and Y, but we're not changing Z. That makes it a little bit simpler, right? 2 axes instead of 3. It's going to move in X and Y, but not Z. It's going to turn on the X motor at the fastest speed the X has. It's going to turn on the Y motor at the fastest speed the Y has. It's going to do both those things simultaneously because it's got individual motor controllers for both motors. The Z also, if you're moving Z, it's the same thing. Starts the motor as fast as it spins. And when it gets to the X coordinate that it needs, it stops spinning the X motor. And when it gets to the Y coordinate it needs, it stops spinning the Y motor. So assuming X and Y move at the same rate, if you were going, it would pretty much go at a 45-degree angle from wherever the hell it is, until either the X or the Y coordinate is correct, and then move
along one of the axes to get to the point. Does that kind of make sense? So that's a rapid move. What did I said we have to learn words so that you can talk to the machinist sometimes, especially when you're young engineers and try to get parts made. So specifically, we call that dog leg rapid. I'm guessing the person that came up with that plays golf. So dog leg rapid, and that's a golf term. But anyway, doesn't necessarily move in a straight line. You could command it to go to an X position, rapid, and then once it's fits in that line of code, you can get to a Y position in rapid, right? So you can make it do the path you want. That would take 2 lines to go. All right. I said there's 3 ways, right? 3 ways we can move. Plus spin the spindle, so there's really 4 ways it moves, I suppose. People argue with me that rotation is motion. What's the third way? We can move it rapid. We can move in a straight line. What do you think the third way is? We can move along a constant radius arc from wherever the hell we are to point B at a controlled speed. So for both the linear feed move and for the arc feed moves, you have to have told it how fast to go. For a rapid move, you just tell it where you want it to be. It moves as fast as it can to get there. That's all CNC machine tools do. The fancy $2 million CNC machine tool and the $20,000 CNC machine tool, they all do those same 4 things. Spins now. All right, so you get fancy tool changers. I haven't run it, but I've been there when it was running. A machine with 100 different tool positions. So the mini mills you guys use for lab, they have 10 tool positions. The VM2 that you used on the first day, when you're making the Y block, second operation on the Y block, it's 25 tool positions. So there's literally 100, and they make them with could even have 1,000 tool positions. I don't think I've ever seen one that big. But what they use is basically a chain conveyor that goes outside the machine tool. And the tools are sitting on this chain rack, and they just get fed into the machine tool and into the spindle. So they change tools. There's macro programs, you're going to drill a bunch of holes. You can envision that. That's just rapid to above where the hole is, right? And then feed in the Z direction. So you feed the drill down. And so, who's ever drilled a hole in aluminum before? Anybody? Use the drill and made a hole in aluminum? So what do you know about drilling in aluminum?
It wasn't very difficult. I kind of missed the tip a little bit, but I made a lot of little scraps.
So it wasn't very difficult, meaning it didn't take a lot of force?
Right.
Yeah, okay. Anybody else have any observations about drilling aluminum? Yes.
Push down too far, it can work the surface, depending on how big.
If you push down too hard, you might bend the aluminum. Yes, I agree. And that's really trying to apply more feed than is possible, pushing down too hard. Anything else? Maybe so you said it kind of messed up the tip a little bit, right? Yes. And so the aluminum will get stuck inside of the flukes of the drill. The flukes are the spiral bits that come up. The purpose of that spiral of the fluke is to pull the chips up out of the hole and make them go away. If you're doing that same drilling operation with steel, when you're going down, it would just throw out chips out of the hole. In the aluminum, it's about the material properties and stuff. Well, it makes a lot of heat when you're doing cutting. Is that intuitive to you guys? The place where you're cutting gets hot, especially at the chip interface. It gets hot. So what happens when you make metal hot? Expands, right? Thermal expansion. So it actually expands so fast that it gets clogged in the flukes of the drill. And suddenly there is nothing that's pulling the bits out of the hole. And then it just stops drilling, continues getting hot though, because you're still pushing and you're still spinning, and then tool breaks. So what we do to fix that is we do what we call peck drilling. It's like you think it is. You go into the hole, you come out of the hole. You go in the hole,
come out of the hole. Every time you stop feeding down, you break the chip. When you come out of the hole, you pull the chips up out of the hole. If you've got that stuff right, you get the right pack depth and stuff, then you don't have the problem of messing with the tip of the drill. So you've got different processes that CNC machine tools do. So you can tell it's going to pack drill. You can tell it's going to pack drill, and you just tell it a bunch of X, Y locations, and it just moves and it makes a hole at all those different locations. So there's a bunch of different things you can do, but it's all about those 3 different types of motion plus spinning the spindle. So we've got to decide if we've got the stock material, we've got the shape we want, and we've decided we're milling in this case. Then we've just got to decide where do we want the tool to move to, and how fast do we want the tool to be spinning. And so it turns out that there's really 3 primary process variables that we have to control in CNC machining. And so they're the feed, that's how fast we're moving to point B. When we're doing a feed move, either a linear feed or an arc feed. The feed we get to control. The speed is how fast we spin the tool around, or spinning the spindle around, right? Because in turning, we're spinning the workpiece, not the tool. And the depth of the cut. And so these 3 parameters control our ability to make chips. Our ability to make chips controls our ability to make the part. So feed speed, depth of cut. Guessing, not recommended. Carbide, explosion. Remember, in small tools, sounds like that. Now, yeah, except then there's like bits that fly around. And so if you ever watch like a war movie, like to get the ricochet sounds, so it's more of a ding, 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 right, as the pieces fly around. Usually that's followed with a, sometimes there's swear words involved, but that's when the operator realizes that the tool broke and they hit the E-stop. And I'm usually never happy when I have to hit the E-stop because the tool already broke. When's the best time to hit E-stop? Before the tool broke, right? Much better than after the tool broke. But it does vent some frustration. And I actually was diagnosed with a repetitive stress injury in the shoulder. And the doctor, when he diagnosed it, he said, it could actually be from a single instance of making this motion. And I'm like, well, I don't go to rallies and do this all the time, but I do make that motion all the time. Usually diving between students, aiming at the E-stop. And after I found out the cost of shoulder surgery, I started letting machines crash. Turns out it's way cheaper to fix the machine than it is my shoulder. You guys laugh. But that shoulder almost killed me because I was having a heart attack, which started with a pain in this arm, and I just thought it was my shoulder injury acting up. I waited 4 days to go to the hospital. So that shoulder thing almost killed me. So yeah, don't do that. And chill out, dude. Like there's no reason to let stress give you a heart attack. So chill out. Now I do I have this thing I drink at night, it's like magnesium thing. It's supposed to make you calm. Because it turns out the whiskey did make you calm sort of for a while, but it also makes you fat, which is also stress around the heart. So turns out the magnesium powder in hot water is better for you than whiskey. Who would have thunk it? But hey, that's good. What's next? Oh, so there's lots of other parameters, right? If you think about what impacts how well the part comes out, besides feed speed, depth of cut, what else would impact how well your part comes out?
if you're putting your part in the machine tool and you want it to be the right shape, you want it to have the right surface texture, you want to have the quality, right? Remember we said that quality is the most important thing. So we want to have the quality that the customer demanded. What's going to impact our ability to deliver that quality besides feed speed and depth of cut? So feed speed and depth of cut 100% controls how the chip forms on the edge of the tool. That's what makes it so that we can use CNC machining to make our parts. But besides feed speed and depth of cut, what other process variables are there? Things, so process variables are things that we as the engineer or the CNC machinist get to control. Like knobs on the machine or things like that. What other process variables are there that you can imagine in CNC machining? You've all been in front of the machines, you've seen what goes on. What's going to impact our ability to make the part? I already said one. Does the part actually fit inside the stock material? Right, so if you've got stock material that's too short, you may have an edge of the part that you don't actually cut. So is the stock material big enough? That's a process variable. We get to choose it because we choose the stock material. What else? Yeah.
Machine maintenance.
Is the machine well taken care of? So when's the last time you changed the lubricating oil, for example? When's the last time you changed the coolant? So those kind of things will impact your ability to make a good part. What else? Anything else? We're going to spend 3 days next week talking about feed speed and depth of cut. Yeah.
Proper offsets.
Did you set the offset correctly? So we talked about setting the offset in lab, right? As in who broke one of our plastic end mills in lab? Be proud. A lot of people broke. Hands up, be proud. Yeah. It was a turn this year that we thought about that. You know what we used to break? Regular end mills. We didn't do the lab where we intentionally set it so that it would break the end mills though. But was it, so when the end mill broke, did you learn something?
Yes.
Was it worth about, I mean, what did you learn? Explain what you learned when the end mill broke.
You just have to make sure that, like, the path, you know, it's not gonna.
Like what it says it's gonna do is not gonna run into stuff.
Yeah.
Yeah. Anybody else that broke one? What lesson did you learn?
To really check the distance to go.
Right. So what are the 6 things we ask everybody to do every time they run one of the CNC machine tools? Anybody remember what all 6 of them are?
All 6?
Yeah, I know what they are. All right. It used to be 5, then I made it 6. Yeah.
Run the simulation through Esper.
So run the simulation in the CAM software. This tells you what the computer thinks the program is going to do. If you don't know what the computer thinks the program is going to do, it's going to be hard for you to judge whether or not it's doing the right thing when it gets to the machine, right? Also, the CAM simulations will find crashes. Right? If you program stuff incorrectly, it often will find that crash. So simulating the CAM software, what else? There's 2 that go together now, and you've already talked about it, right? It's setting the offsets. You're going to set the tool offsets, so you're going to tell the machine how long the tools are. You're going to set the work offset. You're going to tell the machine where the work is in its boundaries. So simulating the CAM software, set the tool offsets, set the work offsets. Once we've done that, what do we do?
Simulate on the machine.
Yeah, there's a button to simulate on the machine. If the little picture that it draws on the screen of the machine doesn't look anything like what you saw when you simulated the CAM software, what do you know immediately? It's probably not the right program, right? The other simulating machine will also tell you, did you forget to program a feed rate or something like that, or forget to program a spindle speed, which can happen. You can't output the code and have forgotten to put that information in. The machine won't simulate if those things are missing. It'll also tell you, did you clamp the part down too close to the edge of the machine's motion? Can it reach all of the features you're trying to make? So it'll catch those kind of things. Then, next super critical step. Yeah? Reduce the rapid speed. Remember I told you when we do the rapid motion, it moves as fast as it can, which is really good if we know it's not going to crash, right? Because we don't need to waste time.
Customer's not paying for us to wait for the tool to mosey on over to point B before it starts working, right? Customer's paying for that part. But the first time through, it might be nice if we had a chance to hit the e-stop if it did something wrong, right? So we can slow that rapid speed down to 50%, 25%, or 5%, or 100%. So we can have it run full speed rapid. Their percentages on the controller, because not all machines have the same full speed rapid. So this mini mill you're using, 600 inches a minute full speed rapid, which means if you've got a 4-inch long tool in the spindle, it takes just less than a second for the tool to impact the table if it's full speed rapid down from the tool change height. That's full speed rapid. You slow it down, you get plenty of time. 5% rapid. You can go get a cup of coffee and come back and check on it. 5% rapid. At least it feels like that to me. But the mill drill center, which is one of the machines in the other room, 2,000 inches a minute, full speed rapid. So 25% rapid on the mini, or 25% rapid on the MDC is like 100% rapid on the mini mill. Moves so fast you can't see it sometimes. It's that particular one was a prototype, and they gave it to us because they don't actually want it to go to a customer site. They may, when they went to the production version, they slowed it down a little bit. It goes pretty fast. All right, so what else is going to impact our ability to make a good part? Oh, what's the last thing? Sorry. Check the distance to go, right? That's the step that we have this lab about. Check the distance to go. You're looking at the line of code telling you where it's going to. You're looking at how far it says it's still going to go. And then you're looking inside and saying, does that make sense? And it's just a quick check. And so we have, since we started doing that 6-step checklist, not had any expensive crashes that could not be contributed to somebody having skipped one of the steps on the checklist. And in almost all instances, check distance to go would have caught the crash. Not always, but almost every time. It's your last chance to not crash the machine. There's really two types of machinists, people that regularly run CNC machines. There's two types. There's those who have crashed the machine, and there's the ones who lie about other things too. All right, so everybody, it's gonna happen. Don't freak out. And we remember what we asked you to do to crash your machine. Yeah.
PLA.
Well, yeah, it's all PLA, but they're gonna give you instructions. They're gonna say, go to, I broke this at WPI.edu, send an email to I broke this at WPI.edu. Tell us what you were doing and what was the result. Please include pictures if they're cool. You know, take pictures of the cool broken stuff. What were you doing? What was the result? What's the approximate cost to WPI for your mistake? This is always the operator's fault. Especially if somebody else set it up and told them it was okay. That is definitely the operator's fault, because you shouldn't believe somebody else for telling you it's okay. Especially if I'm the one that tells you not. Because I get distracted a lot. What's the approximate cost of WPI for your mistake? We don't make you pay for stuff. One time I told somebody they had to pay for the thing. One time in 20 years now. I didn't actually enforce it, but I was pissed, so I told. And it wasn't that he broke the thing. It was that he snuck into the lab using a key he wasn't supposed to have, which really wasn't a big deal because the lab was open at the moment. He was just sort of showing off to his friends that he had made a master key for the building. And but he snuck into the lab using the key that he wasn't supposed to have. I get it. That's fine. It's the locks aren't very secure here at WPI, and it's cool to be the guy that made a master key so that you could open the doors. I get that. But also, he then tried to hide the fact that he broke the machine. He totally destroyed one of the probe bodies. Not the tip, but the mechanism itself totally destroyed it. They took it and put it in a different machine, not the one he was using. Took the one from that machine and put it in the machine he was using to try to fool everybody. Like, because everybody knew which machine he was using. And then they find the other machine has the broken probe in it. Right? It's pretty smart, right? Yeah, no, pretty stupid. Turns out they weren't the same generation of probes, so the software was different. So the one that was totally destroyed wouldn't, if it hadn't been totally destroyed, would not have turned on the machine where it was. And the one that was perfectly okay wouldn't turn on in the machine where it was either, because the software is incompatible. And so we discovered the busted one, and we were looking at the controller. We were trying to figure it out, because you're supposed to tell us. That's the only thing we were mad about, is he didn't tell us. And then somebody comes in and says, hey, the probe doesn't work in this machine over here. And we went over and looked, and like, aha, now we know what happened. We did send the police to go to his apartment and wake him up that morning. But that was for him. It was scary. So please tell us. And in the last step, what are you going to do next time to make sure this doesn't happen again? And that's the point of the whole thing is, have you learned? So you broke a like 27-cent pen mill. Was that lesson worth 27 cents to you?
Yes.
Right. So my question for this other guy was the lesson he learned by getting woken up by the cops 2 weeks before graduation, thinking he wasn't going to graduate because we were going to kick him out of school instead, was that lesson to not lie to people about when you broke something, was that lesson worth $2,000 to him? And if it was, then it was money well spent in my mind. Right? So don't feel bad about this stuff. We're going to spend next week talking about modeling these cutting operations. It's going to be 3 pretty intense days. It's like I suppose it's the technically hardest part of the lectures. It's not hard, but it's probably the hardest part of the topics that we talk about here. And we're going to go in depth on the physics of how the chip forms on the edge of the cutting tool, and the things that we can change, the process variables that we can change to make the cutting operation more efficient, and well, to not break the tools. I will see you guys Tuesday, right? Tuesday. And look at that. We only used the first slide. What do the rest of the slides say? Oh, you guys should click on the presentation and watch the video on slide 2. You should totally do that. And yeah, we'll cover all this other stuff next week. That'll be good. Okay. This is the presentation with like 60 slides too. There. So the YouTube has all the slides so people can slow it down and go back to the one they want to look at. Let me turn this off and then.